Downsampling is everywhere. For example, modern autonomous vehicles can stream up to 1.5 gigabytes per second of camera data alone. This is simply too much, given the strict latency constraints required to act in the real world. Given a fixed pixel budget and a much larger number of available pixels, how do we select the optimal set of pixels and then process them appropriately? This is a facet of the active perception problem. Our method is a simple but effective solution for intelligent downsampling, by which we zoom in on the input image, produce a spatial encoding, unzoom to revert any deformations, and then decode to produce the final loss or predictions. This is very flexible and can apply to any task with spatial input and any model with intermediate spatial features. We evaluate in 3 distinct settings, each with a different task, network, and dataset, and show that LZU improves the cost-performance trade-off in all cases. Now let's take a deeper dive into the context of this work. The inception of this area of research happened with a method called learning to zoom. They propose an efficient formulation that, given a 2D saliency map, outputs a warp that zooms in on regions of high saliency. They evaluate their method on gaze estimation and fine-grained image classification. However, their off-the-shelf method only applies to these tasks whose labels are invariant to spatial deformations. Then how do we apply this method to spatial tasks? There do exist solutions for 2D object detection and semantic segmentation. For example, Fovea is a solution for detection that uses a specialized bounding box inverse to deal with spatial deformations. However, this only applies to detection and is also incompatible with certain 2-stage networks that make use of delta encodings in their RPN. For semantic segmentation, there is a work called Learning to Downsample for Segmentation. This uses the same zooming warp to both warp the ground truth label image alongside the input image. Then, losses are computed in the warped space. However, this requires extra regularization on the warp to prevent the model from collapsing to trivial solutions, such as zooming in on easy regions like the sky. Our goal is to devise a method that truly generalizes to many tasks and models. Notice that both previous works avoid explicitly inverting the zoom. This will be key to our framework. Our framework, LZU, applies to any task with 2D spatial input and any model with intermediate 2D spatial features, with just 2 modifications. First, the input image is zoomed in on, borrowing the same methodology as previous works. Then, after the spatial features have been computed, we unzoom to revert any spatial deformations. This allows us to proceed with the rest of the model, making no modifications to the loss or inference procedures. The key to our framework is having the ability to efficiently and differentiably invert the zoom. We need efficiency to maintain favorable cost-performance trade-offs and differentiability to be able to use common optimization methods like gradient descent. Furthermore, we need to be able to do so even in cases where the forward warp has no closed form inverse, which we suspect is the case with the zooming warp. To do this, we approximate the actual zooming warp as a piecewise tiling of simpler bilinear maps. Then, to apply the inverse warp to any given point, we simply need to figure out which tile it lies in and invert the corresponding bilinear map, which boils down to solving a simple quadratic equation. Taking a closer look at our cost-performance curves, we find that LZU improves the accuracy-latency trade-off over the uniform downsampling baseline in all cases, while being competitive with more specialized task-specific methods. Visually, LZU improves performance at the regions of high saliency. It's also interesting to note how the zoomed input images are perceptually clearer even to the human eye.